Hey, Dr. Clark coming at you with a statistics video. I wanted to make a quick video just sort of doing a full example from like a chapter 1 example so you could see what that would look like if you worked a problem from stem to stern. And so to do that, I basically just cooked up a little problem here, spinning pennies, and I thought we could walk through it and you could see what kind of a problem, how would you actually go through and do a complete problem like this. So let's just read through this. So spinning pennies. Flipping a fair coin should give you heads and tails equally often, but what if you spun a penny and saw which side lands facing up? To test the results, a researcher spun a penny 30 times and logged the results to see what would happen. After 30 spins, the researcher observed 19 heads and 11 tails. So what is a research question we could study here? So it's something about spinning pennies here. A question could be, when you spin a penny, do heads and tails land up equally often? That's sort of one way to phrase it. Another way that might push us a little bit better in the direction of statistics would be something like, is the long run proportion of heads equal to 0.50 or 1/2 when spinning a penny? Now you notice we're putting in that statistical language the long run proportion, because what we want to know is when you spin the penny, are you getting heads 50% of the time or half the time or a proportion of 0.5? And now we're using that proportion language. So the parameter of interest here is pi, which is which is equal to the long run proportion of heads that show up when spinning a penny. So now I've defined it as a symbol, and because it's a proportion, I'm using the symbol pi there. The long run proportion of heads that show up when spinning a penny. So that's the idea. What if we spun a penny like 1 billion times in the long run? What do you get? And I don't know what you get because I never spun a penny 1 billion times, so I'm putting it as an unknown thing. Now in this problem, the sample size is 30 spins. That's the data we got, so I would use n equals 30 for the sample size. The statistic is the sample proportion. Now in the sample, we got what? 19 heads out of 30 spins. So that's a fraction, right? So it's 19 out of 30, which if we use a calculator real quick, what is 19 divided by 30? 0.6333. So 0.6333. We'd call that the p hat, right? The sample the parameter is the Greek letter pi, and the sample proportion is that p hat symbol. And we want to rewrite this question as a hypothesis test. Okay, so we have the null hypothesis. Would be something like the coin is fair. You could rewrite that as that pi is equal to 0.50, or you could say the coin is fair. That'd be one way to say it, or the long run proportion of heads is 1/2 when spinning a penny, right? You could write this out in words, and maybe I could be more precise here. Other than the coin is fair, spinning a penny results in heads, tails with equal probability or something. So there's more than one way to kind of write something like this. You can write it in words, or you can write it using symbols, and oftentimes we're going to use both. And you'll notice if you are using symbols, it's important that you have defined what that symbol is. Okay, the alternative hypothesis is, the coin is not fair, something like that, or the long run proportion of heads when spinning a penny is not 1/2. I don't know if heads comes up more often than not or less often than not, so I'm just going to say for my alternative, if we were doing it in symbols, I would want to use the not equal to symbol. Let me see if there's a not equal to symbol here. Not equal to 1/2 or 0.5. So that's the alternative in symbols. All right, so now we've got our hypothesis test written up there. We've got kind of all the setup done. And the next thing is they want us to go to the applet and actually do a test. So let's jump in here to the applet, and it is a one proportion test. And so let's fill in the information. So probability of heads, well, I picked penny, heads or tails, so 0.5, that is my null hypothesis. I'm going to go 30 here because I flipped the coin 30 times. If I click draw samples, it will flip me a penny 30 times and it'll put a dot on 12. I'm interested in the proportion of heads, so that's 0.4. If I do it again, I'm going to get all different numbers. It's going to make this dot plot down here, right? This dot plot. And I probably want to do this not just once or twice, but hundreds of times. Now, of course, we're seeing that 0.5 does show up a lot, but other numbers can show up as well. So maybe I want to run this like 1,000 times. All right. And then I want to see if what I observed in my sample is the kind of thing that could happen by random chance or not. So what did I observe in my sample? 0.6333. Okay, so 0.6333. And I want to click the two-sided button here because I want to see not just to the right, but also to the left, because the penny could be more heads than tails or more tails than heads. So I want a two-sided test here. So you can see clicking the two-sided. And it looks to me like it is certainly possible to get a number as extreme or more extreme as 0.6333. In fact, it happened almost 20% of the time. So that seems totally reasonable for that to happen by random chance. So this number right here, 0.1990, or right here, 0.1990, that is the p-value. That is the probability of getting a result as extreme or more extreme as what we observed in the sample, if in fact the null hypothesis were true. And that's what you need to be able to do. Know how to fill in these, fill in this, draw the line in here. Notice where the line is drawn. It's drawn in at 0.66 or 6333, which is the sample statistic. And it counts the dots as extreme or more extreme, and then also the dots on the other side as extreme or more extreme over here. And it counts them for you, 199. Okay, so that's basically conducting the simulation-based test. So, via the simulation, we calculate a p-value of 0.1990. This means that the null hypothesis is plausible. If spinning a penny is fair, then it is plausible to observe a result as extreme or more extreme than 19 out of 30 heads. That's certainly possible, right? So we're citing the p-value. We might want to say because 0.1990 is greater than 0.05, which is sort of our typical cutoff for having strong evidence. So because this is greater than that, this means, so I like to cite the p-value and cite the cutoff that we are observing. Okay, so that's the kind of result that we might case. It's plausible that the penny is fair. I didn't prove that the penny is fair, but it is certainly plausible that it is. All right, the next question says, would a theory-based test be appropriate? So this is a question of sample size. So is the sample size big enough? And it is, because we observed 19 and 11, quote, successes and failures, and which are both larger than 10. Remember, the validity conditions, that's what we're looking for here. What are the validity conditions on a theory-based test? And the validity conditions are that the number of successes and failures are both larger than 10. So that is met in this case. So because that's met, we can do the theory-based test and then make our result. So let's jump back to the applet here. And how do you do a theory-based test? Where you leave basically everything the same, and all you have to do is click this button right here that says normal approximation. That's what it means to do a theory-based test. And it will draw that normal distribution, and you'll see that our simulated distribution looks very similar to the normal distribution. So that's encouraging us that our theory-based test is appropriate. It calculates a p-value, 0.1442, which is not too dissimilar from 0.19. It's not exactly the same because the theory-based test will often be slightly different than a simulation, but it's close. And we would come to the same conclusion. So maybe we want to write that conclusion down here with a p-value of 0.1442, which is greater than 0.05. We conclude that the null hypothesis is plausible. That is, spinning a penny may result in heads and tails equally often. That is plausible. So we have insufficient evidence to conclude otherwise. And this, you want to be careful. We didn't prove that the penny was fair. We just didn't prove it was rigged or not fair, right? Something like that. Another thing you can do is say the standardized statistic is z equals what? 1.46. 1.46, which is what? Less than 2. So we do not have sufficient evidence to reject the null hypothesis. So again, you can use a p-value and use a cutoff score of 0.05 for strong evidence, 0.01 for very strong, or you can use the z-score of 1.46, which is less than 2, the cutoff, or 3, the cutoff for very strong evidence. And that, of course, comes right here when you click normal approximation. It gives you the z statistic, where basically 1.4 standard deviations to the right of the center of the null distribution, which is not in the tail, right? We're kind of on the edge of the tail, but we're not really in the tail. Over here would be in the tail. All right, and that is how you would conduct a hypothesis test like that in this situation. Every situation is going to have a slightly different setup, but the main setup is this is your null hypothesis here, this is your sample size here, and this is your data, your statistic from the sample. And those are the three key numbers, and you have to know how to put those in and then know how to draw the line and count the dots over here, or let the computer do it if you have the computer. So I hope that was helpful. If you have questions, feel free to stop into office hours or send me an email. I hope this is helpful, and we will see you next time.